Hello Shaler area, we are back again with another physics note video. This time it is note video number 14. We're continuing our discussion on simple machines. In this video we are going to talk about the wheel and axle and the pulley. So what is a wheel and what is an axle and how does it work together? How is two things turned into one simple machine? Well, it's made of two cylinders, essentially. You have a bigger cylinder and a smaller cylinder. The larger cylinder is called the wheel. The smaller cylinder is called the axle. And most of the time when you think of a wheel and axle, you think of the wheel turning the axle, but sometimes the axle can turn the wheel. It all depends on what you're trying to get your simple machine to do. Essentially, these two cylinders are connected. They're attached to one another in some way. So when one turns one time around, the other one also has to turn one time around. And if you think about that, if you have a big circle that's turning around in a circle and a small circle that's also going around, if they both have to go around once at the same time, that means if you were riding on the outer part of the big circle, like if you were, let me draw. If you're out here and you're in here, this big part out here would be the wheel, the little part here would be the axle. Pretend that you were, like a little person standing out here, and there was another person standing in here, and this object started to go around in a circle. Well, which person would be moving faster? If they both end up going around one time at the same time, they both start and finish at the same time, that means that the guy out here, the girl out here, would have to be traveling faster than the one on the inside, because you have a much bigger distance to go around than the person on the inside would. And if you have to start and stop at the same time, then that means you'd be traveling faster on the outside. So you can see already how a wheel and axle changes distance and can alter speed and all kinds of other things. Gears, which you will do a lot of in the high school, are all wheel and axle based. It's all part of wheel and axles. So essentially all these tools here, we have things like a screwdriver. The wheel would be the bigger handle. The axle would be the smaller shaft. So when you turn this and you turn the screw, and then you have a screw on this end, which is another simple machine. Remember, it's really just a wedge that's wrapped around another cylinder, and then the head of the screw is big. So you could also argue that it's also another wheel and axle. Steering wheels, that's easy to think of because it's actually a wheel. You have a big steering wheel, and you have the axle going down through here, which then causes a whole bunch of other things to happen, causes the tires to turn back and forth. This one says here it's a rack and pinion steering gear, so when you turn the long axle, it actually causes a screw to move down here, and that causes your tires to shift. Bigger tires, bigger vehicles require more force to steer. That's why steering wheels on things like Mack trucks are much bigger. They're huge because the mechanical advantage would be then much bigger and would make it easier to turn those big tires. Doorknobs are wheel and axles. There was a student that asked how a doorknob worked the other day. Well, this part's the wheel, and this isn't a very good picture for it. I actually had a remarkably hard time finding a diagram that showed the actual mechanisms of a doorknob. Lucky for you, if you are curious, and your parents don't mind, doorknobs are remarkably easy to pull off and look at and put back together really, really easily. They only go together one way, especially if you don't pull this part out of the door, out the end. If you just take the knob off and look at it, they go back together really, really easy, usually just 2 screws. But if you do pull it off, you have this big knob, and then you have a long axle that sticks out of it. And the axle is not round, it's kind of flat. It's more like a bar. And this thing here has this piece that comes out, and there's a hole in it that's not quite a circle. So the axle on the doorknob is not quite round, and the hole is not quite round. So when you turn the axle inside the not quite round hole, it causes it to do different things, and it moves back and forth because of it, and that's what causes this part to move back and forth and allows you to open and close the door. And the slanted piece here kind of makes it work like a wedge or an inclined plane. You'd be surprised once you really start to learn about simple machines how much they're everywhere. Pretty much anything you can think about that does a job is some combination of simple machines. So how do you calculate the mechanical advantage of a wheel and axle? Well, it's the radius of the input divided by the radius of the output. So if you are turning the wheel to cause the axle to turn, then the input would be the radius of the wheel divided by the radius of the axle. But if you are turning the axle to make the wheel turn, then the axle would be the input and the output would be the wheel. So you have to remember, you have to make these calculations based on how you're actually using the machine. The input end of the machine is the part of the machine that you are like touching and that you are applying force on. The output part of the machine is the other end of the machine, the part that's actually doing whatever, accomplishing whatever task that you would like it to accomplish. Now, if you take a minute to think about the patterns here, this makes total sense because a wheel and axle, here we have our wheel and we have our axle, and I can draw it this way. This could be our wheel and then our axle sticks out here. All right. So if we are making this turn, in which case up here we would be like turning it this direction, for example, this part here is going around in circles, and it's making the part over here go around in circles. But if you think about this, if I'm turning the wheel part, to make the axle part turn, well, why is it the, oops, I didn't mean to do that. Bring that back. So we have to draw it again. There we go. Okay, if it's the radius of the input divided by the radius of the output. So if I'm turning the wheel part, the radius would be the distance from here. Oh, what is this doing? It would be the distance from here to here divided by the distance of the output, which would be the distance from here. Why does it keep doing that? To here. If you think about this, this is just a lever. Think about what's happening. You are applying a force here. Let's do like an orange or something to separate that off. Let's say you're turning it this direction. So imagine if this radius of the input was a lever, and I'm pushing up on the lever here, and because I'm pushing up on the lever here, it's causing the whole thing to turn, but that's causing this to also move this way. So this can be like your effort force. This part right here would be your load force, and this would be your fulcrum. It's just that on a lever, the fulcrum is usually, on the ground or attached to a wall or something like that, and the lever has limited range because of the limits of the lever. But on a wheel and axle, the fulcrum is positioned in the middle, and the lever is a disc, so it can just go around and around and around and around and around. So if we draw it over here, imagine if this was the fulcrum. Here is our object that we're moving, and we're pushing up on it like that. Well, if we were doing the mechanical advantage of this device, well, how do you do a lever? You do the input divided by the output. All right, so, wow, that's a horrible pen to try to use here. It would be, remember, this distance divided by this distance. And that's exactly the same thing that we got going here. We have this distance divided by this distance. So a wheel and axle is really nothing more than a redesigned lever. We've turned a lever into a wheel. I had mentioned really early on in this section of notes that all of the simple machines that we learn about are really just kind of boiled down to inclined planes and levers. And that's just another example. So, here, let's check for some understanding. If two screwdrivers have the same size bit, and driver A has a smaller handle than driver B, so let's say this is our screwdriver, and here's our handle, and that could be B, and A has a big handle. Which one of these would be easier to turn the screw in the block of wood? Well, if it is the radius of the input, which would be your handle, divided by the radius of the output, which would be that part of the screwdriver, well, you're going to have a bigger mechanical advantage on the one with the bigger handle. Oh, I drew those pictures backwards now that I look at the question. Driver A had the smaller handle. My bad. But still, the one with the bigger handle is going to be the one with the bigger mechanical advantage. All right, here we go. Here's a nice little anecdotal story about Mr. Reagle and wheel and axles. So one day I was trying to change the brakes on my car. I just finished changing this is a true story. I just finished changing the brakes on my motorcycle, and I was like, yeah, I can do this with my car. I went upstairs, kind of had planned out. I was going to take Wes down. We were going to do like man-car stuff. I said, Wes, how about you come down, put on your shoes, we'll change the brakes on Dad's car. Well, this is how it went. Which, just to give you a heads up, it didn't go well. So the bolts on my wheels, the bolts on my rims are half-inch bolts. So that works out to be 0.005 meters, since all these measurements, if we're doing newtons and things like that, need to be in the right units. So our half-inch bolts are actually this many meters. They're on really tight. Oh, as they should be, because it's a car. So I grab my tire iron. You know what a tire iron looks like. A tire iron has one of those little things that looks like this, and it's got like a little lug nut on one side, a lug nut on the other side, and it also goes this way. And they're all different sizes because different tires have different size lug nuts. So I had my tire iron, and it is 0.45 meters from end to end. It's about 1.5 feet long. So what is the mechanical advantage of the tire iron? Well, the actual, you could think of this distance. So if this is the thing that was in my car, and this is where the half-inch size comes from, the 0.45 meters would be from here to here, and you try to turn that to make this turn to turn your screws on the lug nuts. So the mechanical advantage, the input is going to be the 0.45 meters, the output is going to be the half-inch bolts. So 0.45 divided by 0.005 meters, mechanical advantage of 90. That's pretty cool. Tire iron increases your strength 90 times to try to take those bolts off. Well, they wouldn't move. So Wes is down there. I'm cranking on this tire iron. Nothing's happening. They're not moving at all. I even got frustrated and started stepping on it and jumping up and down on it, which I wouldn't recommend because then it falls off the wheel. You end up falling on your butt, hitting your head on stuff. So definitely don't jump up and down on a tire iron. So I looked at Wes and I was like, man, I can't get these things off. I even used like an impact gun. I grabbed some power tools with like an air compressor wrench gun that they use in like NASCAR. Like I don't have one quite that nice, but could not get these lug nuts to move. So I was like, all right, Wes, we're going to science this thing out. So I grabbed some 2x4s that I had in the scrap wood, and we slipped them over the tire iron. So if this was the wheel, and we had like the lug nut there, and we got the tire iron on it. I should change color so you can see. We got the tire iron on it here. It's attached to that lug nut. So what I ended up doing was I took some 2x4s and I nailed them or screwed them together so that they look like this. I had one in the middle too, and it slipped this whole like 3 2x4s together, and it slipped down over the tire iron, and it made our lever really long. Now I could push all the way out here instead of having to push here. Now the handle of my tire iron was 2 meters long. Well, I had this thing all rigged up. I had this like 6-foot long tire iron going on in the basement, or in the garage rather. So if I have a mass of 73 kilograms and I'm literally hanging on the end of this, I got my little hands up here and my head, and I'm dangling by this lever that I hooked up on the tire iron, it starts to move. I was like, sweet, Wes, we just scienced this thing out. We got this problem solved. It starts turning. How much force did I actually have on the bolts? Well, the new MA, the new mechanical advantage, radius of the input divided by the radius of the output. Now it's 2 meters divided by the 1/2-inch bolt. Instead of it being 90 for mechanical advantage, it's now 400. So it's multiplying my strength 400 times to try to take those bolts off. Well, what would my input force be? Well, force is mass times acceleration. My mass, 73 kilograms. What's my acceleration? Well, that would be gravity. So 73 kilograms times 10 meters per second squared. The input force was 730 newtons. My mechanical advantage was 400. So how many newtons were actually being put on the lug nuts of the car? Well, 730 newtons times 400 means I was applying 292,000 newtons to the lug nuts on that car. About 66,000 pounds of force on the lug nuts of that car. And it's turning. I was excited. I was like, yeah, we're going to change the brakes on the car. We've been out here for like an hour and a half. And it's turning, it's turning, it's turning. And then I realized the lug nuts aren't moving. We actually twisted the steel on the tire iron. We torqued that tire iron to the point where the steel actually like torqued and twisted. It kind of looked like a Twizzler whenever I was done with it. So disappointed. Those bolts never ever moved. I put everything away. I was like, all right, Wes, time to go inside. He looked at me and said, but we didn't even get the tire off. I was like, yeah, I know I didn't get the tire off. I ended up having to take it down to the garage. They had to break the tires off the car to change the brakes. The lug nuts, I didn't know this, but I do now. The rims are made of aluminum, but the bolts and everything that go through them are made of steel. And 2 different kinds of metals, when you have them under great amounts of pressure and things like heat, like you do in a car, can actually weld themselves together. It's called galding. They make a metallic bond. Remember, we learned about covalent bonds and ionic bonds and metallic bonds? They will actually form a metallic bond and like join together. It's pretty interesting. But that apparently is the folly of having aluminum rims on your car. Wish I would have saved the tire iron. It would have made for a nice visual. All right, so the final simple machine, the pulley. A pulley is an interesting simple machine. It's very useful, and at the same time, very hard to practically use. You need something to hang a pulley from. I always said if I was going to invent something, I'd invent a sky pulley, a pulley you can just stick up in the air and use, because there's oftentimes I'd want to move something, and I'd be like, man, if I had a pulley right there, it'd make this job so much easier. But how a pulley actually works is it's a little bit like the wheel and axle, where it is, you have the circle, but in this case you have ropes that go around it. So the actual pulley itself, this part, it spins around in circles and it sort of acts like that lever again, but the pulley system itself is pretty unique in the way that it functions. Essentially, let me back up and let's read this. Yeah, there's nothing really all that important in there. Essentially, it lets you lift heavy things much easier because of the number of ropes that end up getting attached to what you're moving. So elevator systems work with pulleys. Lots of things on farms work with pulleys, especially when you have to lift something high up into a barn. Cranes work entirely because of levers and pulleys. And wheel and axles if you start to move them around. Doing the mechanical advantage of a pulley system is pretty easy. All you have to do is count. You don't have to do any measuring. You just have to count. But the trick is you have to know what to count. You count the number of sections of rope that actually support the object that is being moved. And there's two kinds of pulleys. There is a fixed pulley, and fixed by this case does not mean it was broken and not repaired. Fixed means this pulley doesn't move. This pulley is attached to a stationary location. So fixed pulleys are static. They don't end up moving. And that's a really important delineation. You're going to see what the next kind of pulley does, because the next kind of pulley obviously moves. So fixed pulleys don't do anything with the mechanical advantage. They don't impact mechanical advantage at all. You would still have to pull the same amount of rope. The speed is all the same. What they do, though, is they change the direction of force. So a single fixed pulley, its only job is to change the direction of force. So if I had a fixed pulley up here on the ceiling and I was lifting this object and I was pulling down, if this was 500 pounds, I'd have to pull with 500 pounds. If I pulled 5 feet of rope, it would go 5 feet up in the air. It's a mechanical advantage of 1. Much like a lever with the fulcrum right in the middle. A movable pulley, though, starts to change things a little bit. And a movable pulley is a pulley that's actually attached to the object you're moving, not to a fixed location. So as you lift the object, the pulley goes up with it. And because of this dynamic of the pulley going up with the object, you end up like shortening all these kinds of distances. You get some pretty interesting physics going on. But to just simplify it all, essentially what this is doing is it's like it's multiplying the number of hands that you have that you can use to lift an object with. So in this case, we have this piece of rope that is supporting the object, and this piece of rope is also supporting the object. If I were to cut either one of these, the object would fall down. That means there's 2 ropes supporting the object. It has a mechanical advantage of 2. Even though you're only pulling on 1 rope, whenever you're actually pulling on this system, it's using both ends of the rope to lift. So it is doubling the force that you are pulling with. When you start to combine fixed pulleys and movable pulleys, you get something special called a block and tackle system. And oftentimes you'll get pulleys that work in kind of like components like this, 2s and 3s together. Sometimes 2s and 3s that are stacked like the other way, like there will be one pulley behind it and another one behind it, not up and down like you see them here. And this is where, for practical application, pulleys get a little bit tough because you have to thread the rope through all of these grooves and these wheels. And if one of them comes off or a pulley flips over, the whole thing ends up getting tied in knots, and it does become a bit of a pain. Some pretty interesting labs, though, when you get it to work. But to actually set the systems up can be frustrating at times. So let's check these out and see. Let's back up. Let's check these out and see if you could figure out the mechanical advantages. I mean, I realize it's all given to you down here, but the key is understanding why these are the answers. So here we have a fixed pulley, movable pulley. The rope goes up and around, comes down and comes up, and then it attaches to this pulley again. You're pulling here, so I'm going to grab this rope and yank. It's going to make this go up in the air. There's 2 ropes, 2 sections of rope that are supporting the weight of the object. Note, this one does not count. If I cut this right here, I mean, don't use your brains to like think ahead of it all unraveling and that kind of stuff, because that was where I got in trouble in high school whenever I was trying to work with pulleys. This one doesn't count because once you, like if you cut it, don't think about what happens after it goes around the pulley. So just think about direct lines of connection, connected, connected, mechanical advantage of 2. This one over here has 3. Again, this one doesn't count because it doesn't directly connect to the mass that you're moving, but 1, 2, 3, so mechanical advantage of 3. This one's got 5, because now this side of the rope counts, because if we were to cut it, it is directly connected to the system that's holding up the mass. So we're lifting up on the rope here. The rope is going around and wrapping around and wrapping around and touching here. So we have 1, 2, 3, 4, 5. Mechanical advantage of 5. So however much you would pull on this, 5 times that force would cause the rope to go up in the air. Now remember, the trade-off with machines is always force for distance. So if it's going to magnify your force 5 times, it's going to move, it's going to go up in the air 5 times smaller, like 1/5 the distance that you actually pull the rope. So in this kind of pulley system, if I pulled this rope 10 feet, the object would only go 2 feet up in the air. All right, so here we go. What is the mechanical advantage of this pulley system? And how much force would you have to pull on this rope to lift this box? Well, what's the mechanical advantage? How many ropes are supporting the weight of the actual mass here? Well, here's the mass. I see 1, 2, 3, 4. So this has a mechanical advantage of 4. Well, if it's a 100-pound box, how much would I have to pull down in order to get it to move up? Well, if it's a mechanical advantage of 4, it's going to multiply my force 4 times. So I would only need to pull with a force of 25 pounds to lift a 100-pound box. And remember whenever I said pulley systems kind of like multiply the number of hands that you have to lift with? That's kind of like what's happening. So instead of, like if I grab this with one arm and pull with 25 pounds, it is actually taking that force on 4 different ropes, all the same amount of force. So it's like I'm reaching down with 4 hands now and lifting up on the object. So here we have another one. Fixed pulley, fixed pulley, fixed pulley attached to the ceiling, lifting this big, I don't know, we can call it a cement pad or something like that we've attached these pulleys to. Well, what would the mechanical advantage be? Well, how many ropes are attached to the actual mass that we're moving? 1, 2, 3, 4, 5. And does this one count? Yes, it does. It's connected down here to the mass, so that would be 6. So this has a mechanical advantage of 6. If it was 300 kilograms, I would have to then pull with how much force? That's kind of a trick question. Think about how you would answer that. Would you just take the 300 kilograms and divide it by 6 and give me an answer of 50 kilograms? Seems like an easy thing to do, except what kind of measurement is kilogram? It's a mass. I'm asking for a force. So how do you change a mass into a force? Well, F equals ma. What's the A? Gravity. So in the end, instead of it being a 50 kilogram, as you might have thought you would want to answer, you would have to multiply that by the acceleration of gravity to turn it into a force in newtons. So it would be an answer of 500 newtons. So if I pulled the rope 24 feet, if I had a little line here and I yanked 24 feet of rope out, how far would this go up? Well, the distance multiplier, remember, is the reciprocal of the mechanical advantage. So the distance multiplier is going to be 1/6. If I pulled 24 feet of rope out, it's only going to actually lift this 1/6 the distance, so it would only go up 4 feet. Question 3. What is the mechanical advantage of this pulley system? How much force would you need to pull to move the box? And if I pulled 5 feet of rope, how much would the box go up? Well, let's check out this pulley system here. We have fixed pulley, fixed pulley, fixed pulley, fixed pulley, fixed pulley. These ones are fixed to the floor. We have 1, 2, 3, 4, 5, 6 fixed pulleys. Well, how many ropes are actually supporting the object? 1. our mechanical advantage is just 1. This is just an outrageously ridiculous pulley system for really no reason. You'd have to pull with 10 newtons of force, and if you pulled 5 feet of rope, the box would go 5 feet up in the air. And that takes us to the end of Note Video 14. 16 questions. Be ready to be able to look at pulley systems and identify what their mechanical advantage is and answer questions about them. Wheel and axles and all that other fun jazz. Don't forget to fill out the exit ticket, and I hope everyone has a great, super fantastic day.